Yeah.
So today I'm very happy that we have Hadi here to tell us about the factorization homology of a commutative algebra.
Cool. Yeah, and just to add what Sarah said, please ask questions. Otherwise, my talk will only go my talk will only go for a little over 30 minutes. So please ask questions. So let me tell you about why I care about this factorization homology and my motivation. Before I was studying the following map of field theories. So I was studying the map that goes from field theories of dimension 1-1 over a manifold to field theories of dimension 0-1 over the free loop space of a manifold. And I wanted to understand this map using the trace map on algebraic K-theory. The trace map. The candidate choice of R in our case was R equal to differential forms on my manifold, or in more homotopy theoretic terms, this is the spectrum HC to the power of m, this function spectrum. Now, unfortunately, it turns out that the K-theory of HC to the power of m is equal to, is trivial if m is connected. So basically, long story short, I needed to understand these objects better computationally. So I needed a tool to compute THH of differential forms on M. Differential forms on M is THH of C infinity functions. And this thing over here is the factorization homology over S1 cross S1 of C infinity M. And maybe the right target for my map was not supposed to be factorization homology over S1 cross S1, but it was supposed to be factorization homology over S2 of C infinity M. So basically, I needed to compute all these things just to put myself on some footing. Okay. So enough with motivation. Here's my theorem. Theorem is that if I have any algebra over a ring, and these are both E infinity rings, then the factorization homology of A over R is equal to a polynomial algebra over A of M smash derived differential one forms of A over R. Now, I'm not sure if you know what factorization homology is. I'm going to define everything I've said so far. So I'm not sure if you know what THH is. I mentioned that. And so let me just tell you what this factorization homology and THH is. So this by definition is the tensor product of the algebra A with the space M. Here, M is a manifold, which is, I want it to be connected for this theorem to hold. And I'm going to tell you what this tensor product is in a second. A and R are E infinity rings. A is smooth over R. So A is a R algebra and a smooth. Okay, so what is this tensor product over here? So A tensor M, if is equal to, well, if M is the geometric realization of some simplicial set, M bullet, then this is by definition equal to the geometric realization of the following simplicial ring. So I take A smashed M bullet times. So M bullet is a set, so it has a cardinality. So I can smash A with the self M bullet times over the ring R. And I can take the geometric realization of that. So any questions about this definition? Okay. Oh, let me give you an example. No questions. So if M equals S1, then A tensor S1 over R is, well, what is that? S1 is the geometric realization of the following simplicial set. It's Z mod n plus 1 in the nth degree. So the zero skeleton is a point, and so on and so forth. And this accounts for all the degenerate simplices as well. By our definition, A tensor S1 should be the geometric realization of A smashed to the power of n plus 1. Over R. This is often known as the cyclic bar construction. The degeneracies and base maps come from the structure maps in Z mod n plus 1. And it is also the definition of THH of A over R. This A over R just means A relative to R. Okay. Any questions? Cool. So a special case of this theorem yeah, I wanted to say that this theorem is something to be expected because it's a special case of something that is known, which is that the THH of A relative to R is equal to a polynomial algebra over A of the suspension of differential one forms of A over R. And which this thing you should think of as differential forms of A over R, right? Because a polynomial algebra over a suspension is just an exterior algebra, and an exterior algebra over differential one forms is by definition differential n forms. So this is a special case of our theorem when M equals S1. So the M smash becomes a suspension. This theorem over here is independently proved by Hochschild, Kostant, Rosenberg, and also by McCarthy and Manassian for you guys at UIUC, the folks at UIUC. So this theorem is expected. Okay. So with that, let me tell you a strategy for proving this generalization of this theorem that says that THH is the same thing as differential forms. Okay, so the first thing we're going to do is we're going to do a computation when A equals a polynomial algebra over some modulo X. And here polynomial means the free E infinity algebra over the modulo X. So this is pretty easy. It's just it's a straightforward computation. Okay. The second step is to use that A over R is smooth and use an étale descent argument. So let me just tell you what smooth means. So A over R is smooth. A over R is smooth if like spec A is covered by étale opens, and each of those are open inside an affine. So in terms of our ring spectra, we say that we want that the maps from A to we want there to be maps from A to A alpha, where A alpha is some sort of like localization, and maps from a polynomial algebra. This is like the affine into A, and we want these to be étale maps. And I also want these maps from A to these localizations to some sense cover my A. In the following sense, if I have a map of A modules, this is a map of A modules, then it is split. This map has a splitting if and only if it is split locally. Split. This might seem like a strange notion of a cover, but in the discrete case, this is equivalent to a more usual definition. This is equivalent to the union of the specs of the A alphas being equal to spec A. So this notion of a cover is a generalization of the usual notion, one of many different generalizations of the usual notion of a cover in the discrete case to ring spectra. But it involves these Étale maps over here. So we need some sort of Étale descent in order to get from our theorem from the case of a polynomial algebra. So our next step is to look at Étale descent, which says the following. If I have A tensor over R M, and I have an A algebra B, then this is equal to B tensor over R M if B over A is Étale. And I don't want to lose any of you with the word Étale. In my case, all I really want, I'm saying that Étale means that derived differential one forms of B over A is equal to 0. This is something that is satisfied in the discrete case. But usually Étale means something a bit more, but this is all I need in my case. Okay. So to recap, we use this, we prove the theorem in the case of a polynomial algebra, and then we use the Étale descent. We use this fact, which is true in the case of an Étale extension. And that is going to get us our theorem for smooth algebras. Okay. So before I execute this plan, are there any questions? Anything in the chat?
Could you maybe say something about the relationship between E01 EFT and THH?
Yeah. So these 0, 1 EFTs over M. This is like the homology. So 0, 1 is just like things of dimension 0, 1. The one index just as in differential forms. It's like maps from a fat point into your manifold. So this is like the cohomology of well, it's actually, I'm not taking cohomology yet, it's just differential forms on a free loop space. But this thing over here is equal to the Hochschild homology of differential forms of M. So I was hoping that maybe this map from 1,1 EFTs to 0,1 EFTs was the map on differential forms from K theory of differential forms to Hochschild homology of differential forms, but my hopes were dashed.
Okay,
good question. Cool. Before I go on further, I wanted to ask if this tensor product construction over here, this fact about these tensor products descending, if everyone's okay with that. When I gave practice talks, most of the people that I gave practice talks to were like, well, why isn't this true always? What's the connection to Ital? So
I think it would be great if you explained that.
oh, cool. Okay. So is this true always? This true always? No. So here's a counterexample. Counterexample. So let in this Ital descent thing, let A be equal to R. In that case, the tensor product of A over A with M is going to be equal to what? It's going to be equal to A, because it's going to be the smash products over here, they're all going to cancel out. So I'm going to get a simplicial set, which is A in every degree, and the realization of that is A. So my left-hand side is going to be equal to B tensor over A with A. My right-hand side is going to be equal to B tensor over R with M. So this thing is true if and only if the map from B to B tensor M, which is induced from regarding B as B tensor a point over R. So this is induced. Yeah, R is A in our case. Let me just be consistent. The map from a point to M induces a map from B tensor a point to B tensor M. And I need these maps to be equivalences. When is that true? This is true if and only if the map from B tensor M to B tensor a point is an equivalence. Or in other words, I want the fiber of this map, which I'm going to call I sub M. I need this fiber to be 0. Now, for you folks that do Goodwillie calculus, it turns out that IM mod IM squared equals this is a linear functor in M. So this is M smash. This is M smash differential one. This is M smash I S naught mod I S naught squared. But what is I S naught mod I S naught squared? I S naught is the kernel of the multiplication map from B tensor B to B. So this is like the I mod I squared that defines differential forms usually. So this is M smash differential one forms of B over A. Now, our fiber here is 0. So the fiber modded squared is also equal to 0. So M smash differential one forms is 0. So if this is true, well, if M is equal to S1 in particular, this means that the suspension of omega 1 is 0. So omega 1 B over A must be equal to 0. So i.e. B over A must be etal. So that is where the etal assumption comes in. Now, is that okay? This requirement that B tensor M to B tensor a point being isomorphism, I'm going to call this requirement this is the requirement of being THH etal. I'm going to rename this thing over here. So this is the same thing as B over A being so-called THH etal. So as we saw, being THH etal implies that B over A is etal, and the reversed implication is true up to completions. Completions. In particular, being etal implies THH etal for discrete rings. But because this is true for up to completions, it's going to be a useful tool for me in dealing with the completion problems that are, this assumption of being THH etal is going to be a useful assumption to deal with completions. Completions. Okay. So with that being said, let me tell you a proof of my theorem if I assume etal descent. So this is a proof of my theorem, assuming etal descent. Okay, so I have my theorem for polynomial algebras. It's So for polynomial algebras, the theorem says the following. It says that my polynomial algebra tensor for R with M is equal to M smash. It is equal to a polynomial algebra over A of M smash omega 1 E over omega 1 of my polynomial algebra over R. Okay, so now I'm going to use my étale descent. So I'm going to smash both sides with A alpha. Okay. If I do that, this becomes I have my étale assumption here. So I'm going to get A alpha smash A alpha tensor for R with M. This thing is going to be equal to P A alpha. There's a property of polynomial algebras I can use here. Smash over, oh, I'm sorry, this A should be a PRX, polynomial algebra. Okay. Now, omega 1 satisfies étale descent. So this is just omega 1 of A alpha over R. Okay, so in other words, we have a theorem for A alpha. Now we're going to use étale descent on this map over here. So let's look at a tensor M and the right-hand side over theorem, polynomial algebra on M, smash differential one forms of A over R. If I smash this over A with A alpha with my localization, then étale descent is going to make this equal to that. And same thing on this side. By the same argument that I used above. Okay, now my definition, my definition of a cover is going to be very useful here. My definition of a cover, which says that if I'm going to split locally, then I split globally. That's going to imply that this isomorphism here, this equality, which I have, that's going to give me a global map. So my carefully selected definition of a cover is going to imply that there is a map from PM omega 1 A over R to A tensor M that induces the above equality. Inducing the equality. using this. That in turn implies that this over here is an isomorphism. So this is an isomorphism, and that is my theorem. Okay, so that's the proof of this theorem. Any questions? Okay. With that being said,
yeah, Hari. So the cover definition. What like are there some examples that satisfy this?
oh, I actually don't know. I want to understand more about that. I don't understand that myself.
What? So you said it recovers like the classic theorem.
Mhm.
So you don't even know like if it in that case. If
Oh,
it
I do. Yeah,
covers-
in that case, I do.
Okay.
So
like for discrete things.
yeah. So for discrete rings, you can check split surjectivity of you can check split surjectivity. So for discrete rings, you can check if a map of sheaves is an isomorphism if it's an isomorphism on stocks, and it is also a surjection if it's a surjection on stocks. For coherent sheaves over an affine scheme, you can check split surjectivity also on stocks. So that's what tells you that if you have a cover in the sense that your spec A alphas cover spec A, then you can check split surjectivity locally.
And so do you think this is not true when you don't have this property? Like, do you have examples where it fails?
I don't actually. So, and I think the reason is that I think I might actually be able to prove that if I have a cover in the following different sense. So if I just want the cover to be faithful, so if I have the property that if I have a map from M to N, and it is a isomorphism locally, then it's an isomorphism globally. If I have that property, I think I can show that. I think I can show that it is a cover in the sense over here. So I just haven't figured out the proof yet. So there is that. Also, there are other notions of covers. Lurie has a definition of a cover which is different, but I think I can also show Lurie's definition is much stronger. Lurie has a definition of a cover which basically says which is suited to an état map, which is governed by pi naught. Maybe I can write some of this down. So Lurie has a definition of a cover. So there are different notions of covers for E-infinity rings and état maps. And each definition of a cover is subordinate to your definition of an état map. So Lurie, for example, Lurie has a definition of etal. So A to B is, I'll say Lurie etal. If pi naught of A to pi naught of B is etal, and the map on pi star is governed by pi naught. And Lurie also has a definition of surjectivity. Lurie has a definition of surjectivity. Which gives rise to the notion of cover. Which is that K to L is surjective if whenever I have a map from anything, this fiber product needs to be, this fiber product here needs to be non-empty. It needs to be non-homotopic. Okay. So Lurie has this definition of a cover. It is it's governed. Lurie's definition is kind of governed a lot by pi naught. My thing is deals with rings that are more general than just being governed by their pi naught. So kind of pick your poison. But yeah.
Yeah, thanks.
Okay. Yeah, sorry for going on a rant there. I just can't help myself. But. Oh, since I went to this rant, I can go on another tangent. Oh no, I won't do that. Okay.
Are there any other questions for Harry?
Oh, thanks. Yeah.
If not, I'll ask one more. So
Yeah.
This is maybe like a broad overview or sort of question.
Yeah.
But I'm not super familiar with the context of the special case of the theorem. So I was wondering what perspective you would take about what's the most useful thing about the statement of the theorem. Of being able to say that your THH is this polynomial algebra.
Yeah. So I guess the right-hand side is pretty computational, but one can ask whether how do I think of the left-hand side of the theorem? And currently, I think of the left-hand side as this tensor product, because this tensor product can be filtered by ideals whose associated gradients has something to do with omega 1. So in other words, we use Goodwillie calculus on this tensor product, but maybe we can also think of this using factorization homology. So this definition of factorization homology in terms of tensor products only works in the case of E-infinity rings. But I was wondering after a question of Connor when I gave a practice talk to him was that about whether I can think of the left-hand side. I can do Goodwillie calculus. I wonder whether or not I can do Goodwillie calculus. Goodwillie calculus. Calculus on this. If I can do Goodwillie calculus with respect to the variable m on that would also enable me to get a factorization homology perspective on the theorem. So I don't know if that answers your question, but that's probably all I know.
Okay, yeah, it tells me in what directions you'd like to continue broadening this. So that's cool.
Yeah, Hari, definitely the key word it would be embedding calculus if you want to do it on the manifold M, because like factorization homology doesn't make sense for an arbitrary space. But that's like interesting because Goodwillie calculus is different than embedding calculus, and so if it would work, that's like saying that being a manifold is really important. Whereas I think you mentioned that like this result actually holds like using the middle definition like for any CW complex.
Yeah.
So I mean, it definitely, if you want to think of it as differential forms, right? You want it to be maybe important that it's actually a manifold. I don't know. But anyways, yeah, nice talk.
Oh, cool. How much time do I have left?
There are 11 minutes.
11 minutes. Okay. Well, since I have 11 minutes, I might as well tell you why tall descent is true. Okay. So let me say, why tall descent is true. So I'm going to use this notation that I have over here of this ideal I sub m. So I'm going to filter both the left-hand side of this and the right-hand side using similar ideals. So I'm going to take a tensor m to A, and I'm going to call this ideal I sub m A. So I have B smash over A with A tensor R M modulus ideal. And then I have this thing modulo the ideal squared. And this thing modulo the ideal cubed. Okay. And the associated gradeds are this is A, this is B over here. And this associated graded is equal to B smash over A with M smash omega 1 A over R. And for this, I'm using what I've gleaned over here about IM mod IM squared being linear. So the fiber of the map from this mod squared, this modulo the ideal is I mod I squared, and I mod I squared equals m smash omega 1. And the associated graded over here is going to be b smash over a with m smash omega 1 a over r smash to the power of 2. And then I mod out by the h sigma 2 action. So I compare this tower to the tower for B B tensor over R M. And over here, I'm going to have B tensor over R M modulo I M B. And this modulo, its cube. And the fibers over here are going to be, this is going to be B, this is going to be M smash omega 1, B over R, and this is going to be M smash omega 1, B over R, smash 2 times over B tensor M. So état descent applied to this omega 1 is going to tell me that the stages of the tower are equivalent. So the stages of this Goodwillie tower, this is actually a Goodwillie tower. The layers are n polynomial. So the stages of my tower are equivalent under this induced map. So that implies that the limits of let me just say the completions of both of these guys are the same. Equals the completion of B tensor Rm. Yeah. So which raises a point. I don't actually know that the état descent holds. I only know that it's true up to completion. But if I add another assumption here to my theorem, then my theorem is going to be true. So I'm going to need A to be connected. And I'm going to add in my definition of smoothness, I'm going to make this a finite map. A finite. So this is going to be a finite as a module over A, and I'm going to make this THH etal. So that's going to help with convergence stuff. So the B, so the B being connected implies that the B tensor M is complete. And also the B over A being THH etal implies that B tensor M being complete implies that A tensor M is complete. And the finiteness assumption, B over A being finite, that's going to get us that the left-hand side over here is complete. So these extra assumptions, which I just added in here last minute, that's going to deal with all my completion issues. So that is, I guess that's everything I wanted to say.
Okay, great. Let's take a moment to thank Hadi for the talk.
Oh wait, I have 3 more minutes, right?
Well, still thank you for the talk. What specifically do you want to add?
Oh, well, so those are one set of assumptions under which my theorem is true. But another set of assumptions under which the theorem is true is the following. So Akil Matthew Akil Matthew showed in 2016 that if A to B is Lurie et al., it's if A to B satisfies this very strong notion of et al., in my view, unreasonably strong, then et al. Descent holds. Okay. It's an isomorphism. And there are no completion issues because Lurie's definition says that everything is governed by pi naught. So there are no completion issues. And as we saw over here, if we know et al. Descent, then the theorem is pretty much automatic. So this implies the theorem in that setting. If my maps that define smoothness over here are just et al. In the sense of Lurie, then my theorem is true. Okay, so yeah, so two settings in which the theorem is true. Akil Matthew actually only proved this for m equals S1, but I think the proof is not too hard to generalize to any finite CLB complex. So I think my time is up now. So thank you.
All right, and with that, let's thank Hadi again.